So as I was saying, the hydrogen atom or a hydrogen in a hydrogen-like atom, the wave function of an electron
Sir,
would in
you're
the ground
not
state would behave
presenting.
like this. Okay, is anybody saying something?
Sir, you're not
Yeah,
presenting.
I was. I stopped. Okay. Well, I wasn't presenting from the beginning, or
No, sir, you were. You stopped before recording.
okay, somehow it stopped. I didn't stop it. Oh, maybe. Oh, it kicked me out. Actually, when it starts recording, it kicks a few people whose connection is bad out. So it decided that I must be kicked out. The I meaning the presentation. Me. Okay. So now we have this screen. Okay, so the point I'm trying to make is the wave function, the trial wave function has been chosen taking into account the basic physical features of the system. At least we expect the electrons in the helium nucleus to sort of behave like single electrons in hydrogen-like system with a charge Z, but not exactly Z, because the other electron will screen the charge of the nucleus. So we expect to get better results if instead of capital Z, we use a value which is smaller than capital Z. Something which will take into account the fact that the other electron is screening it. Okay. Now, this gives us a family of wave functions parameterized by the parameter Z1. But when we calculate this, we calculate the expression value of H, which includes the expression value of H1, that of H2, and the expression value of H12. All three of these. All three have to be calculated. You cannot calculate the expectation value of H and minimize that with respect to Z1 and expect that to give you anything other than the hydrogen atom result if you did not include the expectation value of H12. By the way, if you had done the calculation without the H12, then it's obvious that the extremization would have happened at Z12 equals Z, right? Why? Because then the family of wave function I have taken essentially would contain within itself the exact solution. If there were no interaction terms, you have two electrons each interacting with a single nucleus, but not interacting among themselves. So that's what I mean by no interaction terms. I mean electrons interact with something outside, but not among themselves. So if that happens, the problem would be that, okay, not the problem, then the problem is really very simple. Then the energy would simply be E1 plus E2, and the ground state energy would simply end up being the sum of the two ground state energies of the two electrons. And then phi R1, phi R2 would really have been the exact ground state when Z1 is equal to Z. And if you did the problem without the H12 expectation value, you would get Z12 equal. So this is without taking that into account. Okay. So we did take this into account. We took the interaction into account in two places. Once we actually calculated expression of H, where we calculated this. In the lecture, I just told you what the value is. I did not tell you how to, but that was in the assignment, exactly how to calculate this. Okay. In fact, the assignment is basically calculating this quantity. It is much of it. Okay. And that was one place where we took H12 into account. The other place was when we talked about phi r, we said that, okay, instead of taking Z, we are going to allow Z1, where Z1 is some free parameter, which I will just allow the variational principle to give me the value of at the end of the day. But we expect Z1 to be sort of less than Z because on physical grounds, we expect the charge to be screened, the nuclear charge to be screened. Okay, so this is partly physics, and then you have to do the maths. But you cannot do that is the whole point in the variational principle. A good variational calculation requires you to actually understand the physics of the system first. Okay.
Okay,
Anything
sir.
else? Yeah.
Yes, sir. I had another question regarding the intermediate normalization thing which you taught in the last lecture.
Mm-hmm.
So I don't understand how can a calculation be considered a convention? You specified something like that. That
No, the
some.
convention essentially, okay. The point is when you do a normalization, do you have to normalize a wave function to 1?
Uh, it's it's advisable you do so.
No,
Yes.
it's not. Well, what do you mean by that? Let's be precise about this. When
So,
you say, suppose when you say wave functions inhabit a Hilbert space, right? You know what an Hilbert space is, right? You have used the language before.
yes, sir.
Okay, so even though the full mathematical version of the Hilbert space is not really necessary for us right now, it's actually quite important in quantum mechanics. But let's think of it this way. One thing which a Hilbert space has to be is it has to be a vector space to begin with, right?
Yes.
And the most important thing in a vector space is that if you add two elements, the resulting thing has to be in that vector space. Okay? In that set.
Yes. Yes.
Now, that is something which, of course, cannot be the case with normalizable wave functions, normalized wave functions only. If we insisted that the only wave functions we will ever deal with are normalized ones, then adding two normalized wave functions will not give me a normalized wave function. Just like adding two unit vectors does not give me a unit vector, usually. Or multiplying a normalized wave function by 3 or any complex number other than something with magnitude 1 will not give you a normalized wave function, right? What
Yes.
is important is that the wave functions have to be normalizable. That is, when you integrate the modular square over all space, you should get a finite number. So that if you wanted, you could normalize them. Okay. Now, when you actually want to calculate something physical out of a wave function, like something like an expectation value, say, that's not the only thing you can calculate. But when you want to calculate the expectation value, you can either start with a normalized wave function and do psi star operator psi integral, or start with an unnormalized wave function and then divide this psi star operator psi integral by the psi star psi integral. That will still work, right? And it's not always convenient to normalize. Sometimes unnormalized wave functions are actually quite more convenient to use, or at least as convenient to use.
Yes, I understand that, but like the calculation which you do,
Hmm.
I don't understand how can it be a convention to just take it as zero, because it should give some physical reality about the situation, right? The values.
The whole point actually of the rest of the lecture, if you listen to that carefully, not a whole point, but a major part of that, when to show that it doesn't really matter. Okay, for the rest of the people who may not have seen that video yet, but you should actually, definitely, should definitely have seen it by now, but many of you may not have because it was uploaded only, I guess, when was it? Yesterday or today?
Today, I guess.
Today, I guess. Yeah. The point she is trying to make is something like this. Okay, let me just briefly give you the background because some of you may not have even watched the video. The problem essentially is that we want to solve the Schrodinger equation, in this case, the time-independent Schrodinger equation for a Hamiltonian H, which is of the form H0 plus V. So the Hamiltonian has been broken up into two pieces. The important thing about this breakup is H0 is exactly solvable. That is what that means is that we know all the eigenvectors and eigenvalues, eigenfunctions and eigenvalues, or eigenvectors and eigenvalues. Okay, you can call them eigenkets and eigenvalues, doesn't matter, for this Hamiltonian H0. And we are going to sort of pretend for the time being that this series is discrete. That is, you have epsilon 0, epsilon 1, epsilon 2, which can be discretely labeled. But even if there's a continuous spectrum here, even if energy levels are continuous, you can just modify the notation a bit and deal with that. So we are not going to bother being very precise about whether this is discrete or continuous right now. But basically, we know all of these and we are assuming, okay, going against what I said right now, but assuming primarily for convenience, not because you have to do it, it makes your life a lot easier, as of course you were saying, that the eigenvectors have been normalized, orthonormalized actually. And we also of course, assume that they form a complete set with this equals to the identity. So H0 is a problem for which the solution is entirely known. And V is in some sense small. Exactly what makes V small, or what would qualify V as small, is something we are going to discuss in later lectures in some detail. That's a rather non-trivial question, actually. But for the timing, let's say we assume that we understand what small means, so we are going to go ahead with that. And so what we want to do is, given this solution, you know this completely, you know all the epsilon n's, you know all the phi n's, can you solve this equation? And the answer is, well, if V, for example, happens to commute with H0, then this solution would be trivial. Okay, you could almost immediately write down the solution in most cases. However, in most situations, we would not commute with H0, and it may be so happen, and usually does happen, that's when we use it. H actually cannot be exactly solved, but we can find a way to solve it order by order, in an order by order approximation. So as long as V is small, we can get a reasonably accurate answer out of this just by keeping your calculations well up to some order. And in fact, most of the really big achievements that say theoretical physics, in this case it is quantum physics, has made, essentially based on things of this kind, where we treat a perturbation as a small perturbation and try to figure out its effects. The way in which you do this basically is you assume that your wave function xi, first of all, you start by doing something rather, well, not rather arbitrary, at least something which looks a bit arbitrary. You say H, which is H0 plus V, you just introduce a parameter lambda in front of that. So that, of course, when lambda is 0, you get back the free theory or the exactly solved theory, H0. And when lambda is 1, you actually get the theory you want to solve. The only reason why lambda is useful is that it helps us keep track of how many potential energy terms you are getting into your expressions. And so if V is small, the larger the number of V's you have, the smaller this thing is going to be. At least that's the way we think about it. So basically, this is the beginning, but then we assume that our ket xi can also be written down something like this: ket xi 0 plus lambda times ket xi 1 . So xi 0 is basically, given the fact that when lambda is 0, xi becomes xi 0, we expect xi 0 from the very beginning to be an eigenket of H0, which is of course what the H becomes when lambda is 0. But these terms essentially are correction terms to the ket. So if you start with the eigenket of H0, and you say that you switch on the perturbation, that is, you start making lambda different from 0 and ultimately tune it up to 1. And as you do that, these terms essentially will give you higher and higher orders of corrections to the wave function, and what usually is more interest to us. But you can't do one without the other, so both are actually important. Lambda en1. So you're assuming that you can write down the wave function and the ket and the energy En in this form. And when you do this, you plug this back into the equation and you get something like H0 plus lambda V into this whole xi 0 plus this whole thing is equal to En0 plus lambda En1. So this is all in today's lecture, at least the lecture which I uploaded today. Some of you have already seen this before, because not the whole lecture, because at least 2/3 of the lecture is essentially something which I gave last year. So some of you, I know, took a look at those lectures before. This was for the last year's course. But there have been modifications made. At least the last part I've added an example at the end, so it's not the same lecture exactly, but it's sort of the same thing. It's an extension of that thing. Anyway, when you write it like this, what you do is then you compare order by order in lambda and write down a series of equations. For example, if you want lambda to the 0, you just look for which terms don't have any lambda here. If I wrote down the next term and so on, it should be easy to see that the only term which does not have lambda is H0 get psi 0 on this side. On this side, the only term which does not have lambda is En0 psi n0. And if you claim that this equation, this psi and En has this form, and this should work for all values of lambda when h is h0 plus lambda v, at least for all values of lambda between 0 and 1, then you have to conclude that h0 psi 0 must be En0 psi n0, and then you get equations like h0 psi 1. That's this equation. So that's one part of lambda, but that's not the only single part of lambda term on the left. On the left, you have two terms which have power lambda. One is h0 psi 1, the other is plus v psi 0. On the right, you have equation En0 psi 1 plus En1 psi 0. So this is just what you get when you compare the coefficient of lambda to the 0 on both sides. This is what you get when you compare the coefficient of lambda to the 1 on both sides. And then you go on. You can keep on adding more and more, higher and higher powers as you go by. Okay. For a rather accurate calculation, you would have to actually add quite a few powers. And there are certain tricks which makes the calculations easier. We are going to discuss them in future lectures and so on. But what was being pointed out here is ultimately these equations allow you to find out the perturbative terms. That is, you can find out psi n0, you can find out psi n1, psi n2, and so on. Okay, I'm actually making a mistake at this stage. I really should not say psi n0 at this stage, or I shouldn't even say En. I should just say E0. At this stage, I should really start by saying E0 is sorry, this is not E0, sorry. This is E0, E1, E2, and so on. And then you get equations like this. H0 psi 0 is E0 psi 0, H0 psi 1 plus V psi 0 is E0 psi 1 plus E1 psi 0, and so on. Those are the equations that you get, and you get higher and higher order equations after this. And using these equations, you can find out the correction terms E1, E2, E3, and so on, and psi 1, psi 2, psi 3, etc. as well. Okay. Now, what is being referred to is the fact that ultimately it turns out that you can find out psi 1 almost completely. You can find out E1 very easily, but when you try to find out psi 1, E1 is rather easy, and that's of course in the lecture. When you try finding out psi 1 of course is a vector in the vector space, so it can be written down as basically this, right? Phi m Is that okay with everybody? All I've done is just put in an identity. So if you know these overlap quantities, which are of course just numbers, if you know them, then you can find out psi 1 completely, right? And it so happens that from the equations that we just wrote down, it takes a bit of slightly clever manipulation to find out equations which will tell us what phi m psi 1 are. Except for one thing. If the level you are perturbing is the nth energy level, and you are trying to figure out what happens when the energy changes slightly from there and the wave function changes slightly from there, then it so turns out that your perturbation theory will give you all these coefficients except for the one for m equal to n. That is, phi n will be multiplied by phi n psi 1, sorry. But that is the number which perturbation theory will simply not tell you. The rest of it, whatever numbers are sitting here for m not equal to n, you actually can figure out all these coefficients from the perturbation theory. Okay? So that is why the point is you don't even know what psi 1 is. Exactly, you don't know what this term is. You know most of psi 1. You know psi 1's projection in all the other directions of your Hamiltonian eigenbasis. That is H0's eigenbasis. But you do not know its projection in the direction of the vector that you're trying to perturb. This is something which perturbation theory will simply not give you. Okay? And that is why you have a scope for a convention now. Since psi is a little first order in lambda, psi is psi 0 plus psi 1. Notice that you do not know this term in psi. So the psi in perturbation theory, even to first order, there is a gap in your knowledge. One piece you do not know. Which is why you can now say choose whatever convention you want to normalize. It doesn't matter. It will give you different results for your final psi. Okay? If you choose two different normalizations. And they are really different results in the sense that one wave function is not an exact multiple of the other. Remember, in any case, if you ask me, given this state of the system, what is its wave function? There is no unique answer to that. You can, given any wave function, you can multiply it by any complex number whatsoever, you still get the same state. However, this is more than that. You actually have a bit of lack of knowledge, let's say, about psi. But the point I'm trying to make is this. It can be shown that it does not matter for any physical calculation. For all physical results, this lack of knowledge about psi 1, a piece of psi 1, will not matter. I showed that in the lecture. Okay, I did not show it completely in the lecture, but I did show that when you tried to calculate the second energy correction, you actually needed psi 1. Okay? So it might seem that if your psi 1 is not completely known, then there will be a piece in your calculation for E2, which you will not exactly be able to find out. As it turns out, that part exactly cancels out and you are left with a result which is unambiguous. So the point is, anything which is experimentally observable, not only for energy, for expectation values of other operators and so on, you can show that you will not get any ambiguity there. Perturbation theory, despite not being able to tell you exactly what the wave function is at every order, still gives you perfectly good results for experiments. That is why there's a convention involved. That is, since the psi is not exactly given to you because of this unknown piece, whether you normalize psi to 1 or don't normalize psi to 1, it's up to you. You don't have to normalize it to 1. And then if your psi was given, then your norm would have been, then the norm would have been fixed, right? Then there would be no convention which you could use. I guess was that the point you were trying to make? That a given ket must have a given convention. Yeah?
Yes, sir.
Yeah, the point is, when you're doing perturbation theory, you cannot find psi exactly. There will always be a piece in the first order, even more than a piece in the second order, even more in the third order, which you will actually not be able to find out exactly. In fact, it looks like a bit of a mystery when you are looking at it order by order. It turns out that basically what the terms which you're missing, or essentially, if you were to add them back, it essentially gives you a phase shift to the entire wave function. That is not so obvious when you're looking at it piece by piece. It becomes obvious only when you look at the full expansion.
Okay. Okay, I understand.
Okay?
Okay.
Okay, next. Any other questions? From variational principle, from the calculations that we have asked you to do? Okay, if you have no questions, then it's my turn to ask some. Usually the threat gets people to ask questions. Okay. It seems the threat was not enough. Okay, so we did discuss things about the variational method. And you must realize that when we were doing the variational method, there was a bit of art involved. Art in the sense that you have to choose the variational wave function properly. If you did not choose it properly, your results would come out to be rather nasty. Okay? Now, everybody is clear about the temple argument? I thought that would, if people have seen that, they should have questions about it. It's one of those advanced things which you don't find in most textbooks. Anybody here know what the temple argument is? Or temple procedure is? Okay, this silence is making me a bit uncomfortable. When I say temple, I mean this, of course, this is not where you go to pray. With George Temple, the person who found a rather nice way of figuring out a bound for the variational method. Has nobody even listened to that lecture? This is the lecture just before before today's, the previous one. Yeah, just tell me that I'm still here.
Yes, sir.
Okay, I'm still here. Thank God for that. Or whoever. So
Sir,
yeah.
sir, in Temple's method, why you take E2 instead of E1? I cannot understand.
Okay, good. That means you have gone through that argument. So basically, Temple's method hinges basically on this. You start with the ket H minus E0 acting on psi. Psi is some arbitrary ket. Okay. So about the H minus E0 acting on that gives you some ket. And this is, of course, a bra corresponding to that. Times H minus E1 psi. So these are basically you're taking two kets. Let's call them phi. Okay, let's not call them phi 0. Phi has been used for other things. So let's call it chi 0. Chi 0 is H minus E0 psi. And so what we are really looking at is this overlap chi 0, bra, chi 1, chi 1 ket. Okay. And it's very easy to see that this thing really becomes, after you sum up n equals 0 to infinity, it is assuming psi has this expansion in eigenkets Cn phi n, then this is going to be Cn mod squared and this, of course, while this sum is formally from 0 to infinity, you could just as well write this from 2 to infinity, right? Because the because for n equals 0 and n equals 1, both terms are 0 anyway. Now, that's one. Now, this was what we use, and then we use the fact that if we are going to assume that E0, E1, E2, E3 are in that order, then this has to be greater than or equal to 0. Why? Because the two terms for n equals 0 and n equals 1 are 0 anyway. For all the rest of the terms, this thing is a positive number, and En minus E0, En minus E1 are both positive factors. So you end up by adding a lot of positive numbers together. So this is greater than or equal to 0, and this gives rise. If you expand this other side, it's easy to see that this is h squared expression value minus E0 plus E1 times h expression value plus E0 E1 and this is greater than or equal to 0. And then we rewrite this as an inequality and use that to figure out Temple's bound. That is, we managed to show that ultimately the energy level E0, the ground state energy, has to be more than this. So this tells me that, okay, I already know that it's less than E psi or less than or equal to E psi, right? Because curly E psi, remember, is our notation for the expression value of H. And the variational principle tells us that this is, of course, less than curly E psi. And this is telling me it's more than curly E psi minus sigma by E1 minus E psi. So if you can make this term small somehow, then this gives a tight bound within which you can confine your E0. E0, of course, is a definite number. That doesn't depend on what family or wave function or what you are using. But you are trying to estimate that actual number by doing this variational calculation. And you are getting an interval from E psi to E psi minus sigma by E1 minus E psi, in which E0 is sort of confined. So if the width of this interval is small, then you know that your answer is a good answer. That is, it is rather tightly bound on both sides. Okay. So for this, the best thing to do would be to try to make this thing as small as possible. Now, how can this be small? Either by sigma being small. Of course, for sigma to be small, you have to choose your family of wave functions carefully. And the other thing is E1 minus E psi should be large. Okay. If it's large, then you will get a small gap. Yeah. Now, for the problem that we talked about in the class, in this, which was Hamiltonian was minus half d2 dx2 plus x to the 4 by 2. Okay, so not the harmonic oscillator potential, an anharmonic oscillator because of the x to the 4 term, and something which you cannot exactly solve and work out. Okay, so we use the variational principle to find a bound for the energy. That in fact was done even in the lecture before that, if I remember correctly, and that gave us an upper bound for what the ground state energy is going to be. Now, for the lower bound, what we did was we took the same family of wave functions. Psi of x was is 4th root of alpha by pi is a minus alpha x square by 2. So the standard Gaussian family, motivated by the fact that the harmonic oscillator, of course, has the Gaussian wave function for a particular value of alpha equal to 1 as an exact eigenfunction. The quartic oscillator, of course, is different, of the harmonic oscillator. So you don't expect this to give you exact results, but you should expect this to give you a reasonably good fit, given the fact that alpha, well, by changing the alpha, you can change the width of the function, and ultimately, the physical feature that you want these functions to have, that the wave function dies out at infinity and all that, they're all maintained by this. Okay. So next, what the question was about is this. When we took the bound, what we did was we took this family, we calculated sigma, calculated E psi, which is rather easy to do. We then calculated sigma, which took a bit of work. In fact, none of the work was done. It was all stated. The answers were given because all these integrals are really rather trivial integrals. You can just sit down and work them out. Okay, by the way, it really means that you have to sit down and work them out. Doesn't mean that you... science, of course, is not a spectator sport. You cannot just benefit from it by hearing somebody else talk about it. Unless you work on it, it will simply not penetrate. Okay, so you have to do the calculations yourself after you sort of understand what is being done. But having said that, the first thing I did when I worked out the example is that I said instead of E1, I can take E2. That is, instead of taking the ground state of the instead of taking the first excited state of the anharmonic oscillator of this H, I was taking the first excited state. Not the first excited state, I was taking the second excited state. So the energy which I put in was E2 and not E1. And the question which is being rightly asked is why? So let's go back to this. Here, why did I choose this particular combination H minus E0, H minus E1? Why didn't I say choose H minus E0 psi and let's say H minus E4 psi and take their overlap? I could have done that, right? What's so special about E0 and E1?
You need a tight bound, sir.
Yeah, but notice that the bound has E in the denominator. So if I can put in E2 here instead of E1, which I did, by the way, when I did the calculation, then the denominator becomes larger, right?
Sir, but then we'll be getting the other energy eigenvalues between the 0th and the 4th one, and that is not exactly what...
No, we already know that. Look, we know if we could carry through the whole calculation the same way, we would essentially end up by a statement which says E0 is bounded by E psi. I already know it's less than E psi, right? And if this thing comes out to be less than E psi, which it is, by the way, so it's a bound for E0. So we are done. Now, I think you may be saying the right thing, but I'm not very sure whether you're going about it the right way. Just to point out, if I had taken H minus E0 here and H minus E4 here, that is, if I just change this to a 4, how would this expression have changed? Because of course a 0 to infinity. How would this have changed? Would this have been the same? Of course it wouldn't have been. I'm calculating a different thing here. So what would this be like? By the way, that this is actually equal to this. Forget the 4 now. That H minus E0 psi, H minus E1 psi overlap is this expression. Is this something that requires you to think about it, or can you just write it down immediately? Yes? So anybody here who can just work it out on your head that this is going to be this? Not this, of course, with E1. That is to say, remember psi is Cn phi n. So H minus E0 psi, what is that going to be? H minus E0 is a linear operator, right? So it's going to just skip across the sum, skip across the Cn and go and directly hit the phi n. And you're going to get what?
En minus E0.
You're going to get En minus E0 times Cn, right? En H hitting psi would have H hitting phi n will give you En. Remember, these are all H eigenstates. By the way, the notation has changed from the variational context to the perturbation context. Today, in today's lecture, we said H0 has a spectrum which is labeled by phi 0, phi 1, phi 2, phi 3, and so on. And H's eigenstates were called psi. But in the variational method, psi was any arbitrary eigenkette for us, any arbitrary ket for us, not an eigenkette for H necessarily. In fact, it was a family of kets, any one of them. And phi 0, phi 1, phi 2, phi n were used for the eigenkets of H. So this is what you're going to get. And H minus E4, for example, that would be simply En minus E4 Cn phi n. Or you may want to write Cm phi m because you want to take an overlap of these two soon. But now if you take the bra corresponding to this and hit that by the ket corresponding to this, or basically take the inner product of these two vectors, that's exactly what it means. That is, you take H minus E0 psi, H minus E4 psi, which is nothing but the inner product of these two vectors. It's obvious that because phi n and phi m are orthonormal, when you multiply them term by term and just add, only n equal to m terms are going to survive, and you're going to be left with En minus E0 into En minus E4 into Cn mod square, sum over all n. Just like you had En minus E0 into En minus E1 Cn mod square for all n. But now comes the important question. When I use E1 here, I could claim that this is greater than or equal to 0. Is that okay? But can I do that now?
So could you repeat the last statement?
So what I did was earlier, the whole idea behind the Temple method was you start with this quantity, you write it in a form like this, which of course is basically, well, here instead of E1, in my version, I will get E4 here, wherever E1 is. But the important thing is the right-hand side here is definitely positive, right? Or at worst, it can be 0. It cannot be negative. Is that okay with everybody? That was the basic idea behind the Temple argument. And then you could use that to figure out that E0 will come. So there's an E0 sitting here. You would have to manipulate it a bit, and ultimately you'll end up with this inequality. Okay, but the starting inequality is that this thing is greater than or equal to 0. Why? Because this sum has to be greater than or equal to 0. Is everybody sure that they have understood why this sum is greater than or equal to 0? If you are, just tell me you are. No problem. That is the sum that we started with, En minus E0 into En minus E1 Cn mod square, sum over all n from 0 to infinity, is greater than or equal to 0. That is the inequality that really was the base of the problem, base of the method. Will that inequality also hold for this?
No, sir.
So
Because
not?
for n equal to 2 or 3,
Yeah. Then it's, you're right. Not even 2 or 3. In this case,
Then
n
it's
equal to 1,
negative.
n equal to 2, n equal to 3. The one I have written down. For n equals 1, En minus E0, of course, is positive. E1 minus E0. But E1 minus E4 is negative, right?
Yes, sir.
So n equal to 1 will give you a negative contribution, n equal to 2 will give you a negative contribution, n equal to 3 will give you a negative contribution. Okay? All other terms will either give you 0, n equals 0 and n equals 4 will give you 0. All other terms will give you positive. But if you have 3 negative terms and a lot of positive terms, that cannot guarantee you that you're going to end up with a positive result. You may end up with a negative result, right? So this inequality will not work. Okay? It may be true, but you don't know for sure. Is that okay? Here, on the other hand, you know for sure they are going to get greater than or equal to 0, 0. Why? Because the two terms which could have given you trouble were 0 and 1, but 0 and 1, these factors are 0. For all the others, 2, 3, 4, and so on, En minus E0 and En minus E1 are both positive, and Cn mod square times that, of course, is a positive number. You're adding a lot of positive numbers together. And there is a convergence sum, so situations like that famous Ramanujan identity of 1 plus 2 plus 3 plus 4 being minus 1 by 12 doesn't even arise. You add up a lot of positive numbers and it converges to something, you have to get a positive number. But then the question is, what? Suppose I started with H minus E0 psi and H minus E2 psi in the calculation. Again, this would just be En minus E0. Actually, it's conjugate of En minus E0, but En and E0 are both real. So it doesn't matter. En minus E2, Cn mod square. Is this guaranteed to be positive?
For this set of wave functions, yes, because we are trying to find out the ground state energy and we know that's an odd function, so E1 coefficient should be 0. I mean, the set of family.
Okay, you are almost perfectly right, except that you use the wrong word. The ground state we know is an even function, right? When you say that is an odd function, which one did you say it means an odd function?
Yes, sir, sorry, sir.
Yeah, so you mix up the even and odd, but your idea is basically right. The point is, there's only one possible term here which will give you a negative contribution. Which is that? The n equal to 1 term is E1 minus E0 into E1 minus E2 to C1 mod square plus higher order terms. All these, not higher order terms, higher terms for higher n. The n equal to 0 term is not there, n equal to 2 term is not there. They're both 0 anyway. And n equal to 3, 4, 5, all these terms are positive. So even this term is not guaranteed to be positive always, but it is guaranteed to be positive in under one situation, which is, when is this term guaranteed to be positive? This whole sum, not this term, not this term, but the whole sum.
When C1 is 0.
When C1 is 0, exactly. So if you know that your family of wave functions that you are using for the variational calculation, they are all orthogonal to the first excited state, then you know for sure that C1 is 0. Right? Is that okay? And how do you know that they are all orthogonal to the first excited state? That's exactly what you said right now. C1 is 0. This is a symmetric Hamiltonian. Remember, the Hamiltonian has minus half d2 dx2. That's always symmetric under x going to minus x. Plus x to the 4 by 2. That's symmetric under x going to minus x. Right? Okay. So two terms which are symmetric under x going to minus x. So the potential is symmetric under x going to minus x, which means here the eigenvalue functions will be even odd, even odd, even odd in that succession. So the first excited state definitely has an eigenfunction which is an odd function. Since I took as a family, there's a family of Gaussian functions which are all even functions, then all of these functions have zero overlap with the grounds, with the first excited state. I do not know what the first excited state is. It's of course not an exactly solved problem, so I don't know what it is. But what I do know is that it's an odd function. So as a result, what you're going to get is a 0 value for C1. And that means that this whole calculation, the same calculation will go through, except that instead of E1, you can use E2. So there are two aspects to this. If I could use E2 here instead of E1, that makes my life even better, right? Because it makes the denominator of this term larger. E2 is, of course, further away from my expectation value E psi than E1 is. So larger denominator here, meaning smaller quantity here. So tighter bound, right? So that's one, and that's the big advantage that we have. And the other one is here we know that E1 that C1 is going to be 0, so I can just as well use E2. So does that answer your question?
Yes, sir.
Of course, if I could somehow figure out a way of making, say, a family of wave functions orthogonal to both the first excited and the second excited state, then I would be even better off, because then I could actually get this even and get an even tighter bound, right? Because E4 minus curly E psi would be even larger in that case. By the way, there was something else in the calculation where even after putting in E2 instead of E1, the whole point is we do not know what E1 or E2 or any of these are, right? Because this is not an exactly solved problem. So we did something else. We replaced E2 by a value which definitely is smaller than it. I know it's smaller. Okay, so I use E2. I don't know what E2 is, but I do know it's smaller than something. So I do know that E2 is larger than something. So I can always put that value in. That would give you a denominator which is actually not as large as the actual denominator, but slightly smaller than that. And what that tells you is that our bound, the real bound, is even tighter than what I'm going to get. So if I can manage to get E0 within a tight bound by doing this, I'm sure that the actual value is even closer to E psi. And as it turns out, the variational method does give you a pretty tight bound in this case. And by the way, just as it was the case for the helium atom, even here, well, in all cases, if you use a slightly more complicated or a bigger family of wave functions than the ones you have used, then at the expense of calculating more, you should be able to get closer to the actual results. Okay. So, for example, when people use variational method to estimate ionization energies in, say, quantum chemistry, they use much more complicated eigenstates. But I'm a bit surprised that nobody raised a question about the helium atom thing, which is one question which I thought everybody should have asked is this one. In the helium atom, the variational wave function family that we took was this. If I interchange R1 and R2, what happens to this wave function? Yes?
It's the same.
Remains the same, right? So this is symmetric well, not just R1 magnitude, R2 magnitude interchange, but if you were to swap the two vectors R1 and R2, we would get the same value, right? So isn't there a principle of physics which says that can't happen?
Are you hinting at Pauli exclusion principles, sir?
Well, I'm hinting at what was the actual reason behind the Pauli exclusion principle. Pauli exclusion principle is a consequence. Okay. Although very often people call this the Pauli exclusion principle as well. But you're right. That's exactly what I meant. Electrons are fermions, right? Yeah, somebody was trying to say something, I guess. I
Yes,
couldn't
sir.
hear.
But this is just the physical wave function that, like, we haven't considered the spin state over here. So
Uh,
that might-
again, bad choice of words, because if you say this is just the physical wave function, you're not taking the spin states. It shows your prejudice against spin, right? It tries to seems to imply that spin is somehow unphysical. Of course, it's not. Spin is as physical as your position wave function. If you can look, the only thing that spin is not is that it's not intuitively obvious what it means, but neither, for example, for that matter, is a wave function. Let me be okay. Let me be very blunt about one thing. If anybody asks me in this class about what is the physical meaning of this result, then I will have to challenge you to first tell me exactly what you mean by physical meaning. Okay, because that's the kind of thing which people often ask: what is the physical meaning of this, and what is the physical meaning of that? Frankly, when you say physical meaning, what you usually mean is intuitive meaning, what your intuition about physics is. But you have to realize that your intuition about physics has grown from what you see around you. And quantum mechanics deals with a world which is so far away from what you see around you, is that neither your intuition nor your language has any words or any concepts that can actually explain these. Now, when you try to sort of explain those things physically, I'm using physically with huge air quotes here. Then what happens is that you usually land up in situations where you end up putting way different meanings to the things than they really have. Especially you end up getting into all kinds of philosophical dilemmas and so on, simply because you're trying to impose your classical understanding of the world. You only have a classical understanding for the simple reason that that evolution has only trained you to understand things in the classical world. Survival of the fittest has put no pressure on you to try to understand what the electron really does, right? So you would have to know, in order to survive in the savannah, whether how fast things can run, or how fast you can run, or how much you can lift. Those things are important for survival. But whether you can move an electron or not, or the way an electron actually moves, is something which is completely alien to your experience, and also your survival. They were dependent on understanding that, which is why it's rather miraculous that by using mathematics we can actually understand that. But when you use the word physical, you have to be very careful. There's nothing physical or unphysical here. Spin is as physical or as unphysical as the wave functions. But you're right. I get what you meant. What you meant was, this is the spatial part of the wave function.
yes, sir. My wording was not correct.
Okay, that's fine. It just gave me a rather nice way of getting into some of a favorite topic of mine. But thank you for that, actually. In addition to that, there's a spin wave function. And because this part is symmetric, you would want the spin wave function part to be antisymmetric in this case. You can actually find a completely antisymmetric spin wave part. You know that if you add two spin halves, you get a singlet state, the 0, 0 state, which is completely antisymmetric in the spin, which is why this happens to be a spin singlet. The ground state of the helium atom happens to be a spin singlet. The spin triplet, if you talked about that is a symmetric spin state that would require you to have an antisymmetric spatial wave function, which of course you can have. And then if you did the calculation, you will get an energy which is higher than this one. That actually is the first exercise state of the helium atom. And by the way, this idea that you can start by assuming. Okay, let me just ask you one thing, all of you. When you say a particular atom has this configuration, let's say this one. Which atom is this, by the way? Any idea? Anybody remembers
Magnesium.
this? Magnesium, right? Good. If somebody remembers parts of the periodic table. Good. When you say this, what does it mean? 1s2, 2s2, p6, 3s2? I mean, what does it mean in terms of quantum? There's a quantum mechanical statement, right? What does it mean in terms of quantum mechanics?
So number of electrons in the different orbitals.
Yeah, but that's fine. But if you say the electron is in two electrons are in 1s orbital, 2 electrons are in 2s orbital, and so on, that means that you're assuming that each electron has a definite state, right?
Sir, I would
Okay,
say
let's
two of
talk about something
the
simple. Let's say 1s2, 2s1, 3 electrons. What would the wave function for this system be like?
sir for each electron, we can write something, some function of phi 1 of R1, phi 2 of R2, and phi 3 of R3, and take their appropriate
So
combination.
you say phi 1 for R1, phi 2 of R2, and phi 3 of R3. Where phi 1 is a 1s wave function. Whatever 1s is for lithium, fine. Phi 2 is another 1s wave function. So phi 1 and phi 2 are sort of identical wave functions, but with different arguments, of course. And phi 3 is a 2s wave function. Is that what you're saying?
Yes, sir. And then I will have to take different combinations of those to make them satisfy the Pauli exclusion principle.
Okay, good. So this one, as it stands, of course, will not satisfy the Pauli exclusion principle. Of course, this is not enough. You have to put in the spin along with it, and then you have to handle the whole thing in such a way that you get an antisymmetric wave function. Fine. But now let me ask you this. When you say, in any case, when you say phi 1 of R1, that tells you that the electron 1 is in state 1s, right? Of course, the moment you have to antisymmetrize the overall wave function so that you no longer are able to say electron 1 is in 1s, electron 2 is in 1s, electron 3 is in 2s. What you will only be able to say in the end is that there are 2 electrons in 1s, 1 electron in 2s. That's why the antisymmetrization is essential. Otherwise, you would end up saying things like you can distinguish one electron from the other. We are going to talk about this in some detail later also, because we will need to come back to this issue later. But even other than that, this antisymmetrization only hinges on the fact that this product is actually a solution to the Schrodinger equation, right? And then because the Schrodinger equation's perturbation is symmetric under permutation of 1 and 1, 2, and 3, if you permute R1, R2, R3 around, the result stays a solution. So all of these are eigen solutions with the same eigenenergy, so you can always overpose them. And then pick one of them, which is the completely antisymmetric version. But you must realize one thing. Is it possible for phi 1, phi 2, phi 3 to be a eigenfunction of H? Or, let's come back to our helium problem. We actually use phi 1, phi 2, where phi 1 and phi 2 were the same function, but it's R1, R2 as your arguments. And H was H1 plus H2 plus H1, 2. Will it be possible to have this as an eigenfunction?
No, sir. It is in general not, but we can assume it is close to that.
Okay, the point is, as long as H12 is there, if H12 had not been there, if the electrons had not interacted among themselves, then H1 plus H2 acting on phi 1, phi 2 will give you basically, then it's trivial because H1 only acts on phi 1, right? So this will become phi 2, H1, phi 1 plus phi 1, H2 phi 2. And these being eigenfunctions will give you just epsilon 1, phi 2, phi 1 as a result. This will give you epsilon 1, phi 1. There's a phi 2 outside. This will give you epsilon 2, phi 2, and there's a phi 1 outside. So again, so this will give an energy of epsilon 1 plus epsilon 2. Okay, so without the mutual interaction term among electrons, this product form, whether you antisymmetrize or not, the product form is a solution, is a possible eigensolution, only if there are no interactions. Because there are interactions, 1s2, 2s2, p6, 3s2, etc., these have to be approximations. They can never be exact wave functions or exact descriptions of the quantum system. Okay? Is that clear? This kind of description which gives you individual states for individual electrons, whether you antisymmetrize or not doesn't matter. But electrons have individual states. This kind of thing is only possible completely consistently only when the Hamiltonian splits up into individual terms and there are no interaction terms. If there are interaction terms, this will never be an eigenfunction to the full Hamiltonian. However, what you are saying is exactly right. This is an approximate wave function under the situation where you can ignore the correction terms. Ignore the interaction terms, which usually is a very bad approximation, by the way. In a multi-electron atom, ignoring electron-electron interaction would give you absurd results. Right? And you all know that even when you studied this, you know that the whole Aufbau principle gives you some order in which the orbitals are filled up, right? But if the interactions had not really been there, then all the levels for the given n would have had the same energy. So S and P, 3s, 3p would have the same energy. 3s, 3p, 3d, all of them would have the same energy. Actually, in reality, it's not the case, right? S has much higher energy than P, D is even less. You know that, right? Is it that way or the other way? Which one has more energy?
S is less than P, which is less than D.
Why? Okay, so what I said right now was exactly the opposite of what's correct. S is less, typically S is less than P. But here, you can get a physical understanding of this. By physical, I mean trying to argue from semi-classical ways. So you all know this, right? Why is S less than P less than D? In fact, 4s is so much less than 4p, 4d that is actually less than 3d. That is why 4s fills up before 3d, right? But these are not statements which somebody just wrote down as rules. These were figured out by doing the theory properly. Okay, I will ask you to think about it. These are all chemistry things that you learned in class 12 or 11 and definitely learned again here in these courses. There's a reason behind all this. This, of course, anything which looks like this is an approximation, but when you...
do you mean the number of nodes?
No, I don't mean the number of nodes. I mean the energies. Why is 3s, 3p... Why should 3p be less than 3s? Okay, in quantum mechanical terms, you can think in terms of, say, more oscillatory nodes having more kinetic energy term and so on. That's one way of thinking about it, but I was asking for a semi-classical understanding. Even before people had quantum mechanics, people understood why P is more tightly bound than S. Or, actually wrong, that's wrong, why S is more tightly bound than P. In a multi-electron atom. In a single electron atom, like the hydrogen atom, S, P, D, all of them have the same energy. Now, okay, let's come back to my point. That's an important question. I think everybody should ponder about this because this is something which you have known for quite some time now. So you should now start wondering about exactly what these things mean. But one important thing is this antisymmetrized product of wave functions. Now, which wave functions would you use? If you started with this and antisymmetrized it, you cannot get an exact wave function, but you can get a family of wave functions which do two things, which satisfy at least look roughly like what the system would have looked like if the interactions had not been there. So it's close to what the system is like. And it also has an antisymmetry which identical particles must have. And then we can do simply what is called what we have been doing earlier. We could simply do a variational calculation. We could take a family of such wave functions, then try to figure out what equation this family of wave functions has to satisfy to minimize the exponential value of the energy. And that gives us a way of figuring out rather accurate, well, not exactly accurate, but at least pretty close to being accurate energy bounds and decent wave function approximations. And this is a method which which actually used to be one of the leading methods in quantum chemistry for a long, long time, and is still the one which you start with. This is called the Hartree-Fock method for finding out energy eigenvalues, etc., for complex systems with multi-electron systems where you have interactions. So you start with a bunch of product wave functions which you antisymmetrize, start with that as your variational family, and then try to extremize within that family. If we have time, we are going to, near the end of the semester, we are going to also discuss the Hartree-Fock method. However, I may not, simply because next year there's this atomic and optical phase course which will also cover this, I guess. So that's of course an elective. But I will try to cover this if I have enough time in the end. What I'm trying to emphasize is the variational principle is used way, way beyond just finding out simple energy eigenbounds for some trivial systems. It's actually one of the most powerful and most widespread methods which people have. And as I've explained in the second lecture, despite the fact that our wave functions may be a bit off from the ground state, the energy bounds actually turn out to be much better than what the things look like. And I've explained why. Why is the energy bound much better? In that Gurpahol had raised the question in the last class as to wave functions being quite different and yet the energy bound not being bad. Well, the fact that the energy bounds are actually much better than the wave function bounds, or the wave function can still be far away and yet give you rather nice energy bounds. There's an explanation for that. That's in the first part of that lecture, of the second lecture on variations. Okay, anything further? If not,
Sir,
yeah.
what do you mean by individual states of the electron?
I mean exactly that. If you say 1s2, 2s2, p6, you are saying there's one electron in one state. When you antisymmetrize, you have just lost the information about which electron that is. Is it electron 1, electron 2, or electron 3? You don't know that, but you know there is a 1s level in which there's exactly one electron. That kind of information can be there in energy eigenstate only if the system has really independent electrons. So what we are really doing is the Hartree-Fock method is basically an independent electron approximation. It helps you to build up towards an independent electron model, where the mutual interaction among the electrons sort of shows up like screening factors, like the way we talked about for the helium atom. So basically, it's like each electron is essentially living on its own, interacting just with the nucleus, but with some way in which that interaction is modified because of the presence of the other electrons. So the actual wave function which describes the multi-electron system can never be written as a product kind of thing, even an antisymmetrized product like that. But by doing a variational calculation, you can get reasonably close to that wave function, and if you get reasonably close to the wave function, the energy comes out pretty close. Okay, you all remember that Friday is an exam, right? That means class test. Another deafening silence. You do remember that, right?
Yes, sir.
And okay, I keep on forgetting. I got myself confused. Is it 1:30 to 2:30 or 2 to 3? Which was your time slot?
It's actually from 2:30 to 3:30.
2:30 to 3:30. I have no problems either way. I just wanted to. I keep on forgetting which one you asked for. Okay, so it will be a 2:30 to 3:30 exam. There will be 2 questions. So more time. And I'm going to insist that you upload all of it at the end, but you have to write down the answer within the time interval. That is, you'll get a 2:30 to 3 slot for the first question. Just type out the answer on the page on VLearn by 3:30, and 2:30 to 3 is one question, and 3 to 3:30 will be the other question. No, I'm not giving a gap simply because you want a gap, you can finish earlier. The question should be finishable by within 10 to 15 minutes. And 3 to 3:30 is for another question. You have to write down the answer within 3:30. You can upload both the questions together by 4. But I will only consider your answers if they're uploaded within time. The answers are typed out within time. And any changes you make to your answer after that will simply not be considered. Is that clear now?
So, by answer, do you mean a numerical answer, like the one that you have to type in?
Numerical answer. It could be a formula. Of course, how do you write a formula? You just type it out, whichever way you want. At least it should be mean. Suppose I want to write something like. So give you at least 5 minutes to type out the answer. If the answer is something like alpha square by 4 pi epsilon 0, let's just say you would write alpha square by 4 pi epsilon 0. You can even put in brackets if you want to make it sort of easy if you want to make it easy for me to understand. Just type that out in the box. But I will have to take a look at the upload is important. Without the upload, I will not consider your answer. And if your upload is different from your answer, I'm not going to consider the difference. Then I'm going to consider neither. Okay, so once you are uploaded, don't change your answer. This is not going to help. Okay, but you want to make it look neater by making it fairer or whatever, you get some extra time. Any questions? Okay, if not, let's call it a day today.
The syllabus will include up to which lecture?
Up to variation, end of variation. The syllabus will not
that means
include
the last lecture, the second last lecture that you uploaded, the one before today's.
One before today. Yeah.
Okay.
It will contain all of it, but including previous ones, by the way.
Okay.
Everything we have done from the beginning. I can set 2 variational principle questions, but they will then end up being too hard. Okay. Anything else? Clarifications? Okay. Good. So today, let's call it a day today. Bye for now.